The thing has been hit. It says
Well,
we're live. Welcome everyone now and temporally in the future. I'm the current host of this broadcast, The Memes of Destruction, joined by a very interesting gentleman I had met the other day, Michael, and we had gotten to talking. Say hi to everyone, Michael.
hello.
And we had gotten into a very interesting discussion, and you mentioned a term in a particular way that I hadn't heard before, the vacuum universe.
A
And among, oh, go
polarizable
on.
vacuum.
Okay, the polarizable. That okay. That's there we go. There we. That's why I'm not finding the right things on the Googles. I apologize, but do you mind kind of giving folks maybe just a little bit of some of your background and everything, other places you've been on this internet stuff and things, and just Mike, who are you?
Well, I graduated from WPI with a math degree. It's MIT's little brother. It's just an engineering
Hmm.
college, undergraduate focused. So, bachelor's in mathematics from there. And I hung out at various maker spaces around Massachusetts
Hmm.
and met a lot of people that way and picked up a lot of engineering skills. Also, uh, took various physics classes as well, and then got scooped up into a Harvard startup called Voxelate, and then another
Ooh.
startup after that. Um, and now I'm running my own startup company.
I know, I know. I saw that. Congratulations, man. It's not an easy thing to do. I say this as a former small business owner that totally failed.
Oh,
Uh, but I had a sign. I did so many cosmetic things. I didn't focus on really what needed to be. I also didn't listen to a wise woman.
well,
Live.
I recommend the iCore entrepreneurship program.
Mm,
It's very beneficial. It's run by the National Science Foundation. The idea is to get more technology into actual commercialization, and it's very customer focused. That's how it has to be when you're starting a startup. You need to make sure that the demand is there. So you need to know exactly what your customers want, and you need to know how to ask them that.
that is, see, I came from more of like a corporate sales background and stuff. So those are things that totally go in there because you could list off whatever the bells and whistles or whatever product that you're pitching or whatever, and that might be great. But unless it resonates with that particular person, unless you're actually solving a problem that person has, and maybe the person doesn't hate you, they're more likely to do business with you.
Right.
That's just
You
what
you
I
don't
found.
you don't you don't ask, would you buy this necessarily? You ask, um, like, how much does it currently cost you? What are your pain points? Uh, what what capabilities would you like? And then you go from that. And that way, there's no, oh yeah, sure, I would buy it, but then they don't actually, because it actually makes sense for them.
The worst thing you can get as a salesperson, at least in my experience, is a maybe. If they don't, it doesn't make any sense. Okay, you move on, you explore somewhere else, but then you're like, oh, this person and everything. Just yes or no. Just yes or no. I understand it's not necessarily the best thing for the consumer. Probably contributing reasons why I'm no longer in corporate sales. Oh, hi, Sharati. It's I. Hippies are people too. Hippies are people too. But as far as the polarizable vacuum goes, hold on, I had this over here. You had mentioned that, and I got completely intrigued because I'm tending to think it's probably right. But
Well,
could you give a little bit of an overview, like what's going on with that?
the approach in general is motivated from sort of an engineering perspective, at least initially. So um, the general idea is if you have a solid material like glass, it has a different refractive index than vacuum or air, for example.
Hmm.
Um, so, and we should also start this by saying most of these polarizable vacuum models have actually been uh, checked off the list of possible theories, but the motivation has led to deeper theories of a similar structure, generally speaking. Um, so the early toy models are just that. They're not a complete theory, but the point is to communicate the intuition, and that is if you have a solid material like glass, it has a different refractive index than air. That's
Mhm.
because it has different particles in that physical material that the light interacts with as it travels through.
So
And
so many are going to get knocked to the other way. Go on.
what was that?
Oh, you're talking about the actual speed, the transmission through said
Sure,
material.
yeah. So in the idea is in vacuum, you can define a refractive index using vacuum noise. So virtual particle frequency in some region gives you uh, a refractive index. And that gives you a direct connection from quantum mechanics to how gravity would work. So yeah, I
Oh.
mean that's the fundamental intuition there, and then that gives you that motivates experiments that you can then proceed with that aren't super difficult, like with the particle physics approaches.
Is this some of the things that I've heard about in cosmology with like baryogenesis and stuff like that? Because I keep on hearing being able to measure like the acoustic things and everything. And I'm sitting back and just my Bayesian prior is like, wait. In space, didn't they always say it's like there's supposed to be no sound? Nobody can hear you scream and everything. But if you're coming from perhaps an earlier, more homogeneous state, I mean, yeah, it
Uh,
makes sense.
that
Or am I
sounds
off?
like the word salad a little bit, but
It was.
okay.
As
So
long as there's like physical matter, you should be able to
although actually it would
hear
be
it.
interesting if you had an audible gravity wave. I mean, yeah, you in principle you could have something like that. You could have a coupling between a gravity wave and phonons in matter. Um, but and in fact, what's interesting is the LIGO detector is in the kilohertz frequency, so partially audible. Um, but
Kid- oh,
I mean, those are amplitudes are way too low to have any coupling term really. There would have to be a higher order nonlinearity. But anyway, let's get back to the fundamentals. So
mhm.
let's say you have some uncertainty in some region of space that's defined by basically all of the entanglement around it, all the matter, all the energy, and all of the entanglement too. So your source is not just it becomes not just the matter giving you a gravitostatic field, but you can now produce squeezed states, which are uh, they're quantum like they're entangled states of photons and other matter, um, such that the vacuum noise in various regions is reduced or amplified, and those can travel through space like waves. So at least from my perspective, I conjecture that that could be the graviton right there, and we just overlooked it, um, and went to the higher energy particles and assumed that. But I mean, these squeeze states have been observed. So on top of that, they've been observed. They travel at the speed of light. So um, it seems like that should be the graviton, especially because we assume that the graviton has spin two, and in order to get these squeeze states, you need entangled two, something called entangled two photon states. So you take the two spins of the photons involved, you create something with a higher order symmetry, two spin, or actually with spin two is lower. It's spins are weird. Anyway, um,
'Cause all I know is graviton is supposed to be a spin two particle, or that's what I
right,
hear.
yeah. What
And
that what
I've
that means is essentially if you rotate it 180 degrees, it looks the same. Spin one is you need to rotate it 360 degrees, and spin one half means that you have to rotate it 720 degrees, so twice around, which is unintuitive. Yeah, but anyway, um,
it's kind of like
yeah,
having like a D20 or something like that. However many the number of degrees of rotation, you'll end up getting back to basically a
sort of like
similar.
with the electromagnetism, you got the right hand rule. You have your
Mhm.
fields all with some direction to them. With a squeezed vacuum state, you have a noise envelope, which increases in some areas and decreases in other areas. And that noise envelope is symmetric about an axis. So if you flip that 180 degrees, it still looks the same. So that's kind of,
Ooh,
I mean, that's a
I didn't think about that.
that's a
Yeah.
very cursory explanation, but that kind of gives you an intuition of how it could be spin too. In practice, you need to take an outer product of um, the vectors associated with the wave functions of the two photons, but that's a whole other, that's not as easy to grasp. So,
Does it have anything to do with what I'm showing the good folks here? Probably
huh?
not. This just just on the Wikipedia thing. I'm just seeing different terms. It's like, all right, this to that, mu to that. Um, is that any relation, or is this
Yeah,
trying to just set up?
this is the original polarizable. Well, actually, uh, uh, Puthoff came out with a paper afterwards. So, um, but yeah, this is roughly where the model started, and I think they were trying to use a scalar coupling term and a few other things, but mathematically speaking, you need to talk in terms in order to connect quantum mechanics to gravity properly. You need to connect um, the quantum wave functions to the metric tensor. So um, that's two stages of outer products at some point along the way. So that's, or at least I assume so. Um, but yeah, so you have your electromagnetic vectors. You take an outer product to get an entangled state, and then that entangled state includes the squeezed vacuum state as a component of it. And then if you take that squeezed vacuum state and you take an outer product with itself, then you can get a description of what that is doing to the metric tensor. I'm sorry, I'm not describing it better mathematically. It's
Yeah, oh no, 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 no. Well, here's the thing. Do I know exactly what you're saying? No. Have I heard some of these words used in a similar fashion? As far as I understand, basically just a tensor is basically it's whatever is affecting something. It's okay. I lean against this wall. There's a tension right here. I remove my arm. I crash into the wall there.
but
It's
no, a
basically
tensor it mathematically is a matrix or a higher order
okay.
object. So when I say tensor, I'm talking about like
A matrix,
um,
basically describing like the very intricate things that are going on.
I'm talking about a matrix or a 3D, like, so you have three matrices stacked on top of each other or whatever,
Mhm.
however many higher order objects. So that would be third rank tensor. Then you have a fourth rank tensor, and that's where you get gravity. So it's an extension of the vectors and the matrices. So lots of linear algebra involved there. Um, so, but anyway, so you have this. So yeah, now you have gravitational sources that are gravitostatic, but you have an opportunity with quantum mechanics to manipulate the vacuum noise that, according to this theory, defines your refractive index of space. Now, one thing I should mention is anyone who's more new to this will say, "Oh, but if refractive index is different instead of space-time curvature, then why do we observe a constant speed of light?" Well, that's because in order to have a self-consistent theory with this model, one of the features it requires is that um, the weak force and the strong force and any higher order nonlinearities are just that. They're higher order nonlinearities of the electromagnetic field equations. Which, I mean, if you go look at how they're derived to begin with, you can kind of motivate how you would do that, but that would be a work in progress. But the idea is if particles of matter are in some sense still light, then they're still affected by the local refractive index, and then an observer made out of particles will be slowed down proportionally, so they will always see a constant speed of light because they're not. We're like the what was that Socratic thing where you got the shadows in the cave and people are watching? Well,
Oh, the Platonic shadows. It was
yeah, the
Plato's
Platonic
cave.
shadow.
Yeah.
So we're the Platonic shadows. We're not the observers, sort of.
Or we classify. We like to classify ourselves as the
Or
observers, but
we
we're
are
seeing the
Platonic
shadows.
shadows that have become sentient and are trying to learn what we are.
That's deep, man. That's deep, man. This is why I wanted to talk to you, just because some of those conversations that we had the other day, I'm like, I think this needs to continue. I think there might be some folks out there that would like that. But as far as the speed of light goes, as far as I understand it, it's the Planck length divided by the Planck time. We get
That's
our
interesting.
2.998 times 10 to the 8, which is approximately the speed of light there.
That's why that's been defined that way. Also, we should say so.
I mean,
Yeah,
that's
all of
what
the
that's
measurements
what it is,
associated
right?
with that will also measure a constant speed of light because all of the measurement apparatuses are also made of particles.
Hmm.
So,
Oh, gone.
well, but basically, because we are, so if you have the weak force and the strong force as nonlinearities of the electromagnetic wave equation, if you introduce them in that way, then their solution sets, SU2 cross SU3, etc., those solution sets become the possible solutions to those nonlinearities of the wave equation. You have a set of possible solitons that can exist, which is interesting as mathematically speaking. That's interesting for a number of reasons. But then, yeah, you regain all of relativity because since we are embedded in that refractive index field, you can only see relative changes in that field. You'll see people on the surface of Earth moving slightly slower, or if things approaching a black hole will appear to move slower because they're embedded in a higher refractive index field.
Now, I got to bring this up because Low Spec Linux is bringing this up again. What are your thoughts on the Aether? Because all I know is back in the day, a lot of smartphones like there's gotta be like an Aether, something's going on. And then we had the I forgot that I'm gonna get the experiment name wrong, but basically they were trying to measure if there was a difference depending on where we were, and they didn't actually get anything. So we're like, all right,
The
there's one.
Michelson-Morley experiment.
That's one. That one. Yeah,
Yeah,
but
so
now, go on.
the problem is that when the Michelson-Morley experiment was done, we assumed that because there was no reference frame associated with the vacuum, that the vacuum couldn't have material properties. That we assumed that. We assumed that because one was true, the other was true. Because every material we knew of in reality had its own reference frame. But actually, the vacuum is a material that does not have its own reference frame in a sense.
Again, that's quite deep, man. The reason why I bring that up is just because in more recent years, it seems to be catching on. I know some folks like Dr. Hossenfelder seem to be becoming pretty fond of the idea of perhaps it's not necessarily a vacuum, but a superfluid. So I sit back and I'm just like,
Well, that's exactly what gives you those properties. It gives you material properties without having to have its own reference frame. That's precisely, at least from a mathematical perspective, how you get both of, can have your cake and eat it too, kind of.
what's the difference between that and the Aether?
So the ether was assumed to be a material that has its own reference frame. So like a fluid, like this T here, that can move and it interacts with the matter around it. That was not true. There is not a one chosen reference frame for the whole universe. And that's what was disproven by the Michelson-Morley experiment. But just because vacuum doesn't have a reference frame doesn't mean it can't have material properties. It's just that those material properties must be relative in precisely the way we see with relativity at that point. So you can observe a higher refractive index at a distance. You can see people near a black hole moving slower. But if you go over there, then you will be moving at the same speed that they are because you're embedded in this refractive index field. So you
Ooh,
can't escape
ooh.
that as a person made out of matter, out of standard matter.
I think this might make folks feel like it's necessarily the Mandela effect. I cannot confirm that. I am not a psychologist, but
What?
oh, I'm responding to a gentleman in chat. My apologies. I am supposed to get better at interacting when I'm doing a live stream. I apologize. Let me go through the chat and give our shout outs to Miss Sharati. And yes, Sharati, no, your children will still beat me in discussions because they're children and the sky is the limit and space is the place. As well as we have Mr. Quinn, as well as Monkey, Mark, along with we have got Linux Dizzy. Yes, welcome one, welcome all again. I am joined by Mike here, and we had a lovely discussion the other day, and we would just want to continue it onward. And I'm just learning so much right now. One of the other things that I found that was very interesting because back on this other tab, let me just go right back here, the polarizable vacuum, bring that up. It's talking about electric permittivity and magnetic permeability of basically quote unquote flat space time. So that kind of sounds like what you were talking about a little bit there, or am I off?
Yeah, it's equivalent. So those properties are defined by the local particles available, whether physical or virtual particles. And actually, virtual particles are why the vacuum doesn't need to have its own reference frame, because the virtual particles don't have their own defined position and momentum necessarily. So that's precisely how you get a relativist, well, a relative material kind of. It only behaves as a relativistic sort of thing.
It seems like because this was something that had come up when I had a Mr. Jonathan Garrod on. Somebody was asking about, and I forget the exact way that they asked it, but the way they had asked it, I reformulated as basically as far as electromagnetism and gravity. I mean, I hear folks say, well, it's kind of the same equations, except you replace like a charge with like mass or something like that. And but it wasn't quite the same. Jonathan had told me it's like, well, basically it is similar. It's basically the inverse square law and everything, but it just seems like we're missing something. And I'm just wondering if this might have something to do with it. And I assume that you may feel the same way.
These are probably a piece of the puzzle. As I mentioned, the original polarizable vacuum theory was not a complete theory, and these days the kind of direction that they're going in general is into topological physics. So not quite towards string theory, but in order to have basically they're trying to borrow a lot of properties of loop quantum gravity, kind of.
Okay.
So loop quantum gravity is really nice, and it works nicely for gravitomagnetism, for spinning objects.
Hmm.
So gravitomagnetism, by the way, was detected by Gravity Probe B at NASA a while back. So we know the gravitomagnetism is real. Um, so, I mean, oh, and also we also know that part of loop quantum gravity has to be correct because it's similar in some ways to Mike McCulloch's quantized inertia theory, which recently got positive results. So,
Oh,
yeah, that project went dark immediately after that point. So, no one can interview him or learn about that stuff. It's military secrets now, I guess. But yeah, that apparently works.
that's very interesting. All
Yes.
right.
So the quantized inertia theory of Mike McCulloch people should be researching that a lot, because one of the big things that it fixes is we know that the spin rate of galaxies
Hmm.
um, is too fast, and we assume that that's dark matter.
Dark matter.
But actually, when you apply the quantized inertia theory, you can actually get um, the rotation curve of the galaxies again, and it's correct. And there have been a lot of disputes of that. Um, but he got a positive result. So what can you do? I mean, the other guys must be wrong at that point.
That's very interesting, and Sharadi is taking this all in as you're basically burying me with all this knowledge and everything, and I'm basically just getting buried under the mountain. But I
Yeah,
appreciate that.
it
That's
took Jeremy a long time to get adapted to that too.
well, like I said, because I remember when I heard your voice, and I'm like, I think I've heard this guy here before, just because I listen to a lot of things. I don't always watch. I'm often doing something, but I'm listening. And I have tuned in some of those, some of the Jeremy on the Alien Scientist channel. If that's your type of thing, feel free to check them out. But I remember I really liked it when there was a science things, and once he goes science, I'm just sitting there and I'm like, now I'm like, okay, that makes sense because what you were just doing right there, I'm like, okay, I feel like I've listened to those before, those the similar words with a similar cadence because you know what you're talking about. You've studied this stuff. This is something that fascinates you and it resonates, and I think that's a good thing, especially if you have other things like what was that recruiting? That I recruit the thing that the Institute of Science was doing to try to get more young folks into science, or
The I-Core Entrepreneurship Program.
hmm, okay. Um, yeah, because I hear all that stuff and it gets me really excited. And we have another purveyor of physics. We get Mr. Kenny Lee from the Physics Channel with Kenny Lee. He does a lot of great little videos. He does the experiment. He'll show you how to do these different little things. And just whether it's the harmonic oscillator or just a lot of these other things. And occasionally he'll do the fancy thing. It's like, all right, I'm not going to drop this thing. And sometimes physics professors get very brave. I still see that video. It's like when your professor knows this thing, it's like, hold this weight exactly here. I'm going to stand here, and the bowling ball is going to come within a half inch of my chin. It's like,
Well, if you trust physics, you trust physics.
it's fascinating. But the other thing that really just intrigued me when all of a sudden I clicked on that Wikipedia thing about the polarizable vacuum is another thing that I had come across a while ago. Go back over to our friend Wolfram Alpha. And the interesting thing is if we take the Planck mass times the Planck charge, divide by, excuse me, Planck mass times the Planck length, divide by the Planck charge squared, comes out to 1 times 10 to the 7 kilogram meters per second squared ampere squared, which comes out to be 1 ampere. And
well, I mean, a lot of these connections are simply because of how all of these units are defined to begin with. Looking at uh, Kurt Jemangul's review of dimensionless physics, and I'm looking forward to their his new talk with Sal Pace because um, that concept of dimensionless physics seems to be where this is going. In terms of you're looking at it from when you look at it um, from a refractive index perspective instead of a space-time curvature perspective, a lot of the math simplifies. It's very interesting.
is it because it gives us a frame of reference outside or inside that? Because I'm
Well,
just trying to
it's
think.
just the we're kind of working with the inverse of the math that we're supposed to be using, and well, I don't know. I'm just getting into that myself now. A bunch of papers came out, and I was given a bunch, so I'm reading through it as I speak. So I don't know the details myself just yet, but that appears to be where everyone's going. There seems to be some excitement about it. Um,
Oh, so what seems to be the most exciting part? And could you just kind of go over, maybe give an example of like a dimensionless unit of measure?
uh, where was that paper? I don't have it up right now.
I'm not sure if I can look for it if you give me a couple of keywords.
Let's see. Can I find it?
because right there on Wolfram Allen, I mean, these are the Planck constants that basically we've measured a number of these, and it seems very interesting. But there are other dimensionless.
I found it. It's on archive, thankfully.
Okay.
Let's see
You want to
if we
shoot a
can get
link
it.
into? We got a private chat on the right-hand side of the browser here.
Hmm.
Do that.
So,
All right.
so I mean, yeah, that paper will say it way better than I can at the moment. I'm just starting to read that. I have so many projects on my plate at the moment with the startup company, and but yeah.
Oh, I already like it. It's talking about crystals. I'm sorry, I'm a sucker for crystals and fractal things. But okay, dimensionless physics. We discussed two scenarios of emergent gravity. In one of them, the quantum vacuum is considered as superplastic crystal, and the effect of gravity describes the dynamical elastic deformations of this crystal. In the
So,
other
so
one,
I should say that this concept, he's using crystal in a specific context where are you familiar with crystal defects?
kind of like an ice cube, kind of like when it doesn't
So you
freeze
can
completely.
have dislocations, vacancies, holes, screw. You have screw dislocations. You have planar dislocations. There are all these things that can happen in a crystal.
Mhm.
And what this guy is saying is that you can have those sorts of dislocations, and that ties into torsion and non-metricity. And if you want to get into torsion and non-metricity, the best person to learn that from at the moment, I think, is David Chester. He's done a couple talks on APEC. He's very knowledgeable about the subject. I cannot do it justice like he can, so I'll let him talk
Could you
about
let the
torsion
folks
and
know
metricity.
APEC? That's the is the American Society for Anti-Gravity, or
Alternative Propulsion Engineering Conference. So to get a general sense of what we're talking about with torsion and non-metricity, when you're taking an integral around a loop, a lot of things in physics assume that that value is zero when you take that integral, or that it has a constant value associated with n number of particles within that volume. So if you have a function that you're integrating around, and it's if you want to integrate around the curl of some smooth function, then you will always get zero because it's just a property of the mathematics involved. But if you then have a function that looks like a screw, it has multiple branches is the technical term. So if you have like the complex extension of the logarithm
Mhm.
that actually produces a three-dimensional, it has a surface in 3D that has multiple branches. And if you look up the complex logarithm, actually, it's better to have a picture perhaps.
All right. Oh, and speaking of people that think logs are important, we're also joined by my co-host from the Eigen Rangers channel, Miss Jen Sharp from the Church of Entropy channel. She stressed the things that you're talking about very highly. What was I
Yeah,
looking up again? Sorry. Short-term memory and too many drugs.
apparently that's a big piece of it. I'm just getting into that stuff now. It's a steep learning curve, but I'll get there. But anyway, yeah, pull up the complex
All right. Yeah.
logarithm. Just as
Ooh. Oh, I like what I'm seeing. I'm not saying that this might look a little familiar, but it's looking a little familiar.
maybe go further down.
Oh,
There you go.
ooh.
Yeah.
Oh.
So if you see the complex logarithm, you have multiple branches, and this is related to gauge. This is related to gauge freedoms in electromagnetism and all sorts of stuff. Um, so when you're re-gauging a system, you're jumping between these branches. But the point is, if you have a function that looks like this, if you define
Mhm.
this to be a valid function, and you take that same integral around the function, now you're going to get a non-zero curl, because it's not what was it called again? It was on my phone. Just a minute.
Now, it basically basically you're kind of gauging. I remember Dr. Eric Weinstein at one point, he said, it's like, well, what is sea level or something? And that would depend on where you are. If you're next to the beach, I don't know, the sea level is maybe 5 feet below you. If you're on the top of Mount Everest, it's probably a little further away. So it's kind of like a frame of reference. But as long as you can continue onward and smoothward, like I believe this is what he was attempting to do with geometric unity, basically using those different gauge freedoms to kind of just compact everything together. And at least according to him, it looked like he was getting really close.
Well, I don't know. I haven't been able to. I have been too busy to dig into his theory yet, unfortunately. So I couldn't say if that's the case, but perhaps. I'm trying to find this terminology that's associated with these. Yeah, I don't think I still have it on my phone. Maybe I can look it up with the other term.
This
Sorry,
is
I'm just
very.
trying to be thorough here with my explanations.
Oh no. This diagram, it looks something familiar to something else that I'd seen before. Let me see.
What was that thing?
I think I saw this on something. I think it was a helicoidal collapse.
So it relates to something called Chern-Weil theory
Oh,
and
something with the
Chern-Weil
Chern-Simons.
homomorphisms. And yeah, that's you get there it is. The term I'm looking for is de Rham cohomology, and basically that says when you have defects in your function, you have singularities. In this case, the particles. So when you take some integral around the magnetic vector potential, for example, around a particle.
Yeah.
Now, because of the mathematical concept of de Rham cohomology, when you take that integral, you can get a non-zero value around that, and that's how we get the observable fields, in a sense.
So that technically where mathematically, like kind of the center where my cursor is here, in other forms that would appear as a zero, but utilizing this, it appears as something.
So the idea is that all of the particles have some topological properties, for example, spin, and magnetic vector potential, and scalar potential, the voltage. So these potentials have in principle they have some singularities, and when you integrate around those singularities, you get non-zero values, and that's the only way that you could have a particle with mass that stays. So not only do we have to introduce these as higher order nonlinearities of the electromagnetic wave, but the particles have to be topological structures in a way.
All I know is whenever I see Grothendieck's name, I'm like, we're heading into Topos land.
Yes, that's true.
I was listening to, I forget, somebody was like going over like some tapes that had been transcribed in the notes, and it was like a series of like 11 hours or something like that, where he was kind of describing his ideas and kind of going back and forth, and they kind of reassembled it. I'm like, this is absolutely fascinating, and I feel like these are some of the ideas that kind of led to some ideas within the greater mathematics communities of things like the infinity groupoid and everything, just because, like we're stressing, topology kind of seems like where it's at.
Well, yeah, I mean, these are, again, this is where I'm learning these things as well now. So, but this is where people they have bits and pieces from asymptotically safe gravity. They have bits and pieces from loop quantum gravity, and they have bits and pieces from the polarizable vacuum model. And using topology, that seems to be the way forward.
All I know is,
to bring all of these concepts together and unify gravity. But yeah, I mean, in some sense, though, you can already get the graviton without having to go into particle physics using squeeze states. Because I mean, if you think about it, gravity and electromagnetism both act over very large distances with an inverse square law, and they both travel at the speed of light based off LIGO, like the gravity wave detectors. Gravity seems to travel at the speed of light. So we know that all the other forces are confined to small regions because of the nature of their nonlinearities, because their bosons have, because their force carrying particles have mass. Or they're highly energetic. So the graviton, in order to have all of those properties in common with the photon, must be an entity at low energies. It must be something at low energies. And that's, I think, what these something called squeezed vacuum states are, if you look up squeezed vacuum states.
Because I've heard about that a little bit. I haven't jumped into it. I think I came across, like, I think one article maybe from Quanta or something where they were talking about it more recently. But squeezed vacuum, there we go. You know me, Google, better than I know myself.
Creepy, huh?
Dude, all I know is, like, back in 2013, I just got an iPhone. We were going out for, like, a St. Patrick's Day get together. It's like, well, which pub are we going to? This one. How do we get there? I go on my iPhone. I type in the first word of the second, and it comes right up. I'm like, thank you, Google, for saving St. Patrick's Day. And like you said.
Anyway, let's pull it.
All right, so we stop this. We will share our other screen over the squeeze coherent state is what comes up. Does this look familiar?
Yeah, scroll down a bit.
All right. Ooh.
Keep going.
All right. Ooh. Keep going.
That's good up there.
There.
Yeah, so you have a noise envelope. So here you have a number of states. The top one is just the vacuum state. You have some noise associated just with the uncertainty principle. But now the second one from the top, that is what we call a squeezed vacuum state. So you have noise that is amplified and de-amplified in various regions. And we know that that can travel on its own like a photon can, because in a sense, it is a photon.
It's looking. I'm seeing that screw-like spin, and as far as I understand it, that's
so this is the third is a photon, by the way. The third is a photon, and then the last two are mixes, where you've basically you have superimposed this envelope of vacuum noise that has a wave of its own, sort of, on top of a non-zero photon. So if you entangle two photons that have zero amplitude, in a sense, you get this vacuum state. I mean, that's not intuitive. Well, more accurately, let's say you entangle two photons which are perfectly 180 degrees out of phase.
Okay.
Then their electromagnetic amplitudes will cancel almost perfectly or perfectly. And the only remaining thing will be the noise envelope that was associated with those photons. And now that you can manipulate that noise envelope, and if assuming that noise envelope is what produces refractive index in the vacuum, that gets you a graviton. And you can see how, just like I was saying, if you rotate that 180 degrees, it has a symmetry there.
Now, if you have them perfectly canceling each other out, isn't that technically what, like, an anti-photon? Or
no?
Because I'm sitting there just because, like, whenever I hear, it's like, all right, you got spin, you got opposite spin, so I'm like, all right, something that's different. Usually, just
no. See, because we're not talking about classical electromagnetism; we're talking about quantum electromagnetism.
Okay.
So classical electromagnetism doesn't have the graviton, but as soon as you go to quantum electrodynamics, now you have the graviton inherently in your model, and people overlooked it because it was so obvious that they just called it a squeeze state and moved on, and they thought that, like, they didn't see the connection for whatever reason, or the engineering-wise connection until the polarizable vacuum model.
Wait. So what you're saying is the solution may have just been in front of us the whole time.
Yeah.
I can believe it. Now, okay. So we have these cool things. It's looking very similar. What type of experiments could we do to try to wait without getting into any classified? We're not looking to commit treason or anything here. Just from your intuition.
Well, I'm sure that like, well, first off, like a lot of the experiments associated with squeeze states are public knowledge. So if you wanted to generate your own squeeze states, like you just pick up a textbook anywhere. I mean, there's a number of experiments we've discussed at APEC, Alternate Propulsion Engineering Conference, and just in general on Jeremy's channel. The ideal case is if you have something similar to a Tesla coil, where it's parametrically driven. Now, look up parametric transformers on maybe an image search, so we can get a sense for what a parametric transformer does.
Ooh, I'm looking like the gears of reality here. All right, who was it? Was it Maxwell? Somebody was saying it's like, oh, it's all these gears. Oh, you're crazy. And then I'm start seeing stuff like this, and I'm like, okay, okay. Which one of these may be?
No, these seem to be from some video game or something. Never mind. We will look at.
There we. Oh, that's why Genshin Impact. All right. Science. There we go.
I don't know about. Oh, there you go. There's a Wikipedia page.
All right.
Further down.
Wikipedia, our friend.
Yeah.
All right.
So actually, even better than this, at least to describe the mathematical concept, let's go to John Louis Naudin's page. Look up John Louis Naudin parametric coupling. GEAN, it's French or something. I mean, sorry, JE.
Oh, I'm sorry. I was listening to letters, not words. John. What's the last name?
Naudin. NAU.
NAU?
Yeah.
There we go. Boom.
NAU. Yeah, there we go. Look at the parametric. Also look parametric coupling.
All right. Huh.
So this is also because, well, he claimed a bunch of free energy things could use this. There's a whole other conversation.
Do you want me to go to? It looks like his website or somebody.
Yeah, I think so. Yeah.
Website.
Let's start there.
Okay.
A step towards over unity. That's the one you want. If you go to the top, he has a link to it.
Okay.
No, okay. Maybe it's further down.
I think this is.
Okay. If we go down. No, he doesn't. Parametric
page. All right.
Introduction.
Ooh. All right.
There you go. Perfect. See, this is the complete equation for a transformer coil. You have the standard flux coupling term, but if you remember simple, what was it? Integration by parts? No, what was it? I'm rusty. I've been doing too much hands-on engineering and not enough theory. But yeah. So when you're taking a derivative, you need to take a derivative of all the pieces of that function to be mathematically correct. So when we, in our engineering classes, when we're learning about inductors and transformer coils, typically they'll just give you the flux coupling term, but there's a whole other term by which transformers can transmit energy between circuits, and that's this parametric coupling term. So when you have two transformer windings next to each other, and there's a iron rod between them, then the fluxes are coupled between the coils, and there's a direct induction of current and that's how a normal transformer works. But in a parametric transformer, sorry, in a parametric transformer, you have one winding that's wound this way. You have another winding that's 90 degrees to that. So there's negligible flux coupling terms between the coils. But what they're doing is you can use one of the coils to bring the you have your magnetic material, and that magnetic material can be saturated. So by saturating the magnetic material, you can change its apparent permeability as seen from the other coil. And then any noise in the other coil will be amplified as that permeability changes. So that's where you get the parametric coupling term. And so when you take a transformer coil and you rotate one of the windings 90 degrees to the other so that there's minimal coupling, now you have a parametric transformer. And what that allows you to do is build parametric oscillators, which basically parametric oscillators have the minimum possible. I mean, if you've designed it properly, they have H bar over 2 noise. They're at the limit for the minimum amount of noise that you can possibly have. And now if you drive one of these parametric inductors at twice its natural resonant frequency, then you will produce a squeezed vacuum state straight from there at the radio frequencies. And you can do it with optical systems as well. But if you drive something that's similar to a Tesla coil in this way, then you're going to squeeze the electric field that the Tesla coil produces, the noise associated with that field, and then you can probably measure that with an interferometer of some kind. Maybe the LIGO detector would be required. But it depends, because if you have a very high Q factor, which is that's something in resonant circuits, that's a concept, Q factor. If you have a very high Q factor, you can get very high squeezing, and then you'd see more of an effect. So that is
now the Q is something outside of that. Is it that a derivative of that? Because I'm seeing basically energy equals D over T times Li.
So L is the inductance and I is the current. So the standard flux coupling term, you're assuming constant inductance for the coils, and the di dt term is associated with the actual current in one of the coils. But the parametric coupling term, you're actually modifying the inductance of that the other coil observes, because you're polarizing it in some other direction, and then that extra polarization is no longer left for polarizing in the first direction. So, but anyway, yeah, so you would build one of these, and there's actually something called the topological Tesla coil, which should maximize the effect. So that's where you have a bipolar Tesla coil, where you have 2 poles. You can look up bipolar Tesla coils online. There's plenty of examples. But if you take one of the poles of the Tesla coil,
it reminded me of something I had heard before.
No, not that.
Not the rodent one. Okay.
No, look up a bipolar Tesla coil.
All right. Gotcha. Feel free to continue explaining to the. I'm bad at talking and typing. I'm like Sean Carroll.
Okay.
Polar Tesla coil. But I'm learning so much. This is absolutely fantastic. All right.
Glad to help.
Construction and testing. No. Well, dude, there's all these different perspectives. This is the one thing I've learned about the internet. It's just like there's so many. You're dealing with like 8+ million people in the world. There's going to be all these different folks out there, and especially if somebody has some knowledge that I haven't really explored, or even if it's similar knowledge, but I hadn't just even considered that one little other perspective. It can change a lot. So
that's the internet for you.
Something
when it's properly run and not suppressed.
Properly run, not suppressed, and being able to cycle through noise. Okay, sorry, I forgot I wasn't sharing screen. Something like this, or
yeah, that's an early example.
Not
maybe
a good one.
There's more modern ones where you have a large. Go to like just Google Images maybe. There's some that's there. Yeah, so like on eBay, there's this bipolar Tesla coil. They have these 2 top loads And they have things sticking up from the top loads, but you don't need that. You have your primary winding, and your secondary winding is center tapped. And then you have your two poles on either end of your secondary winding. Now, if you take that structure and you have one of the poles be spherical, and then you have another pole spherical around the outside of the first pole, now you've trapped all of your electromagnetic fields, so you're not emitting any far field radiation. You're only emitting a something equivalent to a surface plasmon, and that's a near field object, but you can still squeeze that near field object, and that's pretty much how you, yeah, that might be how you can get a,
I mean, I'm just listening, Mike, and I'm just going. I'm like, that. It almost sounds like what you're describing. Again, I'm not an engineer or study electromagnetism, but I'm just like, that sounds like a direct alternating current or something.
yeah, so I mean, it's you could think of it as a mixture of AC and DC, but the idea is that because your capacitor plates are circularly symmetric, as you're charging and discharging this thing, the far field stuff is all stuck inside there. But you have a near field component, which is, it falls off exponentially with distance. And actually, there have been a number of experiments that have shown that that near field component can travel faster than light. It kind of steals the property from electrostatic fields. But yeah, that
I'm just trying to see if there was like a better one here.
if you can squeeze that object, then you may be able to produce a Alcubierre-Froning type warp field.
Mike, all I know is if literally the secrets to potentially exploring the cosmos were essentially turned into cheap children's toys at Hot Topic with that globe you put your hand on, and it's like, ooh, look at that. That's so fancy, man. I mean, I'm totally okay with it. I'm just saying, like,
these are some systems you can experiment with to try and get some result using squeezed states. So that's
how would we go about? We would need our particular detectors and I'm trying to think like an experiment.
Yeah, you'd probably need an interferometer. You might be able to. I mean, if you wrote up a nice proposal, you might be able to get time on the LIGO detector to see if there, because that system would almost certainly be sensitive enough. If you can get a good system, that would be sensitive enough to detect these.
Now, is this something hypothetically, if we were able to design something nice and compact, perhaps something for like the International Space Station, or maybe even something outside the International Space Station if you didn't want to F with the equipment? I'm just thinking about what type of box and detectors could we use to maximize our ability to detect the efficacy of the experiment and actually do something realistic.
You might be able to use atomic clocks. If the field, if the gravitational field produced is large enough, you might be able to use atomic clocks. But I haven't gotten gravitational fields that I can feel with my hand yet, so you probably can't do it that way, is my guess. Besides, with a squeeze state, it's oscillating between being squeezed and not being squeezed. So the average speed of light is going to be the same. What you're going to get, though, is you're probably going to get a smearing of whatever interference pattern you're expecting. So as you're using some interferometer, the response time of that interferometer is probably in the kilohertz or lower, and you're probably waving this field in the megahertz. So it's probably your interferometer might not be fast enough to pick up the result, but you would be able to predict a kind of smearing or combination of the interferometer patterns associated with normal and like lower speed and higher speed even. So
we want to use the right tool for the job.
You'd be able to do an interferometry experiment, probably, yeah. And but towards other experiments, the claim from a lot of people working in this is that topological insulators and materials with their own topological properties, um, and things with very high nonlinearities, so nonlinear optical crystals, uh, surface plasmon stuff, or actually no, what was it? A polariton condensates. Yeah, any resonant condensate in matter can have very large nonlinearities, and those large nonlinearities can allow for coupling terms to get you very high squeezing. And well, they say very high coupling with gravity in general. Um, I think a lot of it is a bit hand wavy at the moment because when they're talking about the Prigogine effect and self organization and things that are not at thermodynamic equilibrium with large nonlinearities and all these things, that's just a combination of a whole bunch of terms that just make the equations too complicated to solve. So it sounds to me like just a justification for more research dollars. It's like, oh yeah, we have no idea at all how this works, therefore throw us money. I mean, but
I mean, I'm not saying the model necessarily
it seems,
hasn't worked in the past for
hand
different.
wavy. It seems a bit. So you have some idea that topological physics is involved. You have some idea that large nonlinearities help achieve high squeezing. You have some vague concepts of. By the way, a lot of the thermodynamics, they're saying, oh, things far from equilibrium. Well, there's a lot of self-organizing systems fairly close to equilibrium. So, like, there's the graphene energy harvester at the University of Arkansas now, which, if that's real, that breaks the second law of thermodynamics directly.
Okay, pause. Graphene harvester. Can we go back to what the pierogi equation was, or state, or something?
Oh yes, the Prigogine equation, or sorry, the Prigogine effect, more accurately. Sorry, that is, if you're far from equilibrium with a highly nonlinear system, sometimes self-organization can occur that is unexpected. That's kind of the vague sense of the Prigogine effect, and there's a lot of math that goes into that. But I mean, basically, what they're saying is, oh, there's these self-organizing effects that we don't understand, so we're going to push them along out where the nonlinearities are, where the thermodynamics that we don't understand is, and we're just going to put it there. And like, it's a mess of mathematics to even try to understand it. But like, we can break down this problem into little pieces. Self-organization is a separate property from a lot of this other stuff.
Prigoghine's theory suggests that far from equilibrium systems that fluctuate non-linearly can leap, quotations, across statistical bifurcations into new orders of complexity by themselves.
Yes, so this is in nonlinear systems. This concept of bifurcations is important. So bifurcations, they're like attractor fields. They're related to attractors. So if you have some stable attractor and you have some other stable attractor here, according to Prigoghine's theory, this stable attractor associated with normal entropy and normal thermodynamics, the system can jump into this other stable attractor with another organization to it. So yeah, look, I mean, this there's chaotic attractors, for example, which the human heartbeat is a chaotic attractor. It if you I mean, a lot of this applies to biology as well. It gets close to biology because biology is so nonlinear.
Right,
Yeah,
man.
yeah. I mean, in fact, I would say that the Prigogine effect might even be more important to medicine and biology once people in that field can really dig their teeth into it. It might be more important in that field even than in gravity.
I mean, I have a claim that I've made for a while, And my claim is that if we can solve for universe, we can solve for us. If we can solve for us, we can solve for universe. Those words coming out of my mouth now, I probably need to change some of the verbiage in there. Let me replace universe with arena of operation.
Do whatever you want. I don't know if that's relevant or not.
I'm just saying that basically the complexity that it takes for us to come from some protons, neutrons, electrons, photons, and everything, like even if we could figure that out, it's like, okay, we have the guts of the theory of everything, whatever it is. It's like that's great. Can we still explain like how we got here? Maybe,
Well,
but I'm
all I know
sorry.
is that, this attractor space in nonlinear like physics is a very useful general concept because, for example, you can describe the development of a liver as an attractor associated with a bunch of biological processes and a bunch of boundary conditions.
Okay, cool.
So, for example, if you look at, I think Michael Levin's research, Levin, is he at MIT? I forget. Michael Levin, if you look at he was able to determine the initial conditions required for growing organs uh, and induce their growth.
Was he the guy that grew an ear on a rat?
He grew a planarian with two heads and a planarian with two tails. Basically, you use CRISPR to genetically pattern the natural electrostatic field within the organism, and then the cells use that electrostatic field information to decide what to differentiate into. And in fact, he was also able to suppress cancer with this.
Well, I do
Well,
you know if he was on Sean?
basically, he found that the cancer cells became detached from this electrostatic grid that the cells set up. So
Whoa.
the cancer cells go rogue in a sense because they're not receiving any signals from the rest of their body, so they're just growing and differentiating as much as possible at that point.
So that literally just may be like a desyncing with like some of the greater. Oh, okay. Um,
So yeah, I mean, yeah, you look at his. He has a TED talk. It's quite. He makes it quite easy to understand, but yeah, it relates to nonlinearities. It relates to um, attractor space, and yeah, the attractor space generally that just gives you the set of stable solutions to your nonlinear equations, and the bifurcation is a concept where you have for a linear partial differential equation, you have a function that's the solution if it's solvable. For a nonlinear equation, the solution is some branching structure, and the bifurcations are the branches. So you don't have something that's just like with, in fact, just like with the branches on the complex logarithm. I mean, it's not a great analogy, but similarly to that, you have a multivariate object, not quite a function. So if you look up like uh, nonlinear bifurcations, you'll see like, oh, there's a function that goes in here, and then it splits into two solutions after some point.
so nonlinear. Are are we just basically kind of like going to delve back into like the Mandelbrot set? Because like I feel like this is where we're kind of going, man. I don't know.
I think that some of these nonlinear systems relate to fractals, but um, I'm not very knowledgeable in that space yet. So,
You said nonlinear. What was it?
nonlinear bifurcations.
Bifurcation. All right. Boom. Boom. All right. I'm I'm hearing a lot. Again, I love how this is fleshing things out because like I'll hear things and it's like even the other day I was on the phone with like my stepbrother and I was describing something that Jonathan Garrard had told me that I thought I kind of knew what was going on, but apparently he's like, oh yeah, holography. I'm like, Oh, thank you. And it's just that one little thing that just helps clear things up a little bit better. But
Hmm.
okay.
Well, some images might help. Or yeah, that could work too. Yeah, see, you have multiple solutions like this. And this is not like it's multivariate, so it's not a standard function like you would think of. But yeah, you can have multiple stable branches of this object. And
Ooh.
yeah, it really is just like that example, it relates to chaos theory too. Um,
Whoa, I like that. That's pretty.
yeah, there's a some those are two attractors, for example. Or actually, no,
Hmm.
that's a single attractor. My bad.
I think it's kind of like a Mobius twist there.
Yeah.
Uh,
But, I mean,
yeah,
so basically your system values are for whatever your nonlinear system is, they're moving around in that shape, and that's an attractor.
so there's like a typical pattern, at least within the reference frame of like biology and stuff, and it kind of
Yeah,
sounds
yeah,
like.
and if you have a nonlinear system where your initial conditions start far from this object, if
Hmm.
it's an attractor, they'll try to go to it.
Right.
But if there's another attractor, it'll go to that instead. Or if there's actually stable and unstable attractors. So unstable
Mhm.
attractors are where if you start with your initial conditions near an unstable attractor, it'll move towards a stable attractor and away from the unstable attractor. So both of these things exist.
Is that because the unstable attractor has like a repelling effect, or it's just as
Yeah,
it
yeah, it has
implies,
a
just not
repelling effect.
stable? Okay.
Well, so yeah, generally as you step as you take time steps with your if you think of a discrete like computerized solution, you have your nonlinear equation, you compute your next instant in time, and as you compute your next instant in time, it has these dynamics
Okay. Because I'm literally just thinking about
as
like.
you evolve the system.
Right,
Yeah,
because I'm just thinking, okay, basic experiment. You got a box, you got a crumpled piece of paper, assuming everything is smooth, yada yada, controls. You have literally air blowing in from both sides, assuming everything is equal. If one is intermittent and one is consistent, it's going to go. And I realize that's the opposite of what's attracting. That's the repulsive effect, but essentially the same principle. Whereas if it was going there, but it sounds like it's literally just driving it away instead.
yeah, yeah. I have that book that's over there, Nonlinear Oscillations, Dynamical Systems, and Bifurcations. That one's a good book.
We're bookmarking it.
Down below that, the yellow
I
one.
none. Oh, okay. Hold on. Let me make sure I get there. This one.
Yeah, I got that book.
But
It's I mean, you definitely need to study the prerequisites first, I would say. But
so I
yeah,
need both books.
I don't know if the other one's a prerequisite for that.
Okay.
By prerequisites, I mean you have to be familiar with partial differential equations and some introductory chaos theory, um, at least the concept of attractors and bifurcations, and then maybe some nonlinear PDEs.
Congratulations, Michael. You've tied my brain into a knot.
You're welcome.
I I love, dude. We've been going over an hour. I know you have limited time. Thank you so much for coming on again. Just being able to explore this and do like a little bit of real, and that is one of the things I do appreciate about when occasionally I'll hear you on with like Jeremy or like some of the Wolfram uh streams and stuff like that. They'll literally in real time. Well, we have a question. What do we do? Oh, let's free. No, we have the freaking internet, man. And you know what? Even if you go to Wikipedia for a quick reference frame, you know what? You want to actually get into the archive? Go check the archive. There's probably some links there. Let's go on Google Scholar. Let's actually look at the literature and delve into it. And with Wolfram Alpha, you can actually start to plug it in, and it's
Yeah, I mean one of the big ways that they keep information suppressed is by misdirection these days. So if there's something they don't want people looking at, they'll be like, "Oh, look at this shiny object UFO. It's a balloon, really, but whatever." And then everyone's going to go to that channel and watch that, and they're not going to be like, "Oh, hey, what's this thing called a stable attractor?" They're not going to be looking at that. So, like, a lot of this is well known. A lot of this is well known physics, but if the populace doesn't know the search terms or the context for understanding these things, they're out of luck. They couldn't. If you don't know the search term, you can't Google it, so it doesn't exist to you in a way. That's the shortcoming of Google.
I'm getting vibes from the most recent Doctor Strange film, and it's like I feel like we need to learn the incantation, the particular spell in order to release knowledge and stuff.
So,
I'm not saying that's one of the reasons why I was slightly memeing Jonathan Garrod into kind of a Harry Potter-esque style individual, but
mhm.
that's part of it because, well, if any sufficiently advanced technology is indistinguishable from magic, it's like I say we live in the rise of the technomancer age.
That's got to be a sci-fi novel.
Babylon 5, my friend. Hopefully they do actually start to do a new one. Give the maestro J. Michael
Oh yeah,
Straczynski full
that
reign.
show. I heard that the storytelling was good, although the special effects were awful. Hopefully, something does.
Dude, all the money went to Star Trek and everything there. What they did on a shoestring budget in literally, I think it was like a hot tub warehouse and stuff. With what they did, it is one of the best written shows. Again, the actual effects of everything compared to Star Trek, yeah, it's
Didn't
kind of
Gene
corny,
Roddenberry
but
also write Andromeda? Was it-
I don't I feel like they did. I can't confirm that.
Let
I'm
me
sure the
see.
internet knows.
Yeah, that one's. Yeah, Gene Roddenberry, created by Gene Roddenberry. Yeah, the first few series, the first few seasons of Andromeda are also great, but then Gene Roddenberry died. It's an old forgotten gem. For anyone who likes Star Trek, they should check out Andromeda.
It does have Kevin Sorbo in it, and I started watching it. I end up getting distracted by other things. I didn't know that they had done a full 5 seasons. I only watched the first, and I'm not
Oh
gonna lie,
yeah,
it
some
was
of
kind
the
of
later seasons are terrible though, so I don't
that
bother.
might be why I didn't hear about it
Um,
as much.
yeah, it's really too bad because Gene died, and then his son tried to write it, but did not have the same degree of talent.
Well, it's also different concepts. It's like what's going through my mind is, well, I mean, there's a lot of things. It's usually
Do
ends
you
up
like
in
turtles?
Oh, you're
I'm
memeing now. Okay.
this is me signaling that basically we're wrapping up the show.
Okay,
Uh,
gotcha.
dude, this is like I said, my mind is literally in a knot at this moment, and I'm like, all right, this is the point where anything else, it's just gonna slide off. That's why I'm like
Yeah.
bookmarking like that
Like
bookmark and everything. But
this is a
and
good place
usually,
to cut it short for now.
yeah, and usually this is around the time where if I'm going to talk about science things, it's like, okay, I want to try to absorb and then go back and re-listen and then digest and try to see if I can align up some of the things I've learned as well. But Mike, thank you so much for coming again. Is there anything you would like to promote? Any future appearances? Any particular?
Thanks for
Oh,
having me on. Nothing as of yet. I am collaborating behind the scenes on the Alternative Propulsion Engineering Conference, and we'll hopefully have more positive results soon. I actually, yeah. Did you see? Actually, you should direct people to Jeremiah's um, levitator experiment, or
oh,
even pull it up.
shoot me. What was it?
That
What?
would be one thing to show off. It's not gravitational; it's electrostatic, sort of. But
Oh,
well,
the one the other day. Yeah. No, he was putting actual like massive objects on it.
yeah,
That's why I'd asked. Yeah.
yeah. It's a levitator. It takes the you have a high rise time, and you have a um, DC high voltage and an AC high voltage, and you combine all of these and it levitates because the by modulating all of this, you're causing the dielectric that makes up the table to have a lagging response to the fields. So in that sense, it's analogous to like eddy currents when you're making like a ring of aluminum jump up on a solenoid coil.
What's going on over there, Jeremiah? Oh
Yeah,
yeah.
it's the electrostatic analog of magnetic like eddy current levitation, and it can actually be more
That's pretty
efficient
cool coil shape.
Now
because
that right there, that table is metal-ish,
It's really
or
surprisingly stable too.
I think Nolan or one of our friends in the
I
chat
really want one of
actually had
those.
directed me to this, and
I
I'm
mean, how
like,
much more
this
do
is
you need to
very
crank up this
interesting,
Make yourself
and that's why I
hoverboard.
wanted to ask him because it's not gravity, this is electrostatic. But dude,
Hoverboard.
that's
yeah. So there's a few claims about this.
They actually made one for a commercial.
My working hypothesis, is that it's electrostatic in nature, and because you're driving it with AC and DC, you're causing basically the dielectric particles have some field associated with them. That
it kind of like what you were saying before, something about that parametric term, or
this one is not parametric. This is not. This isn't even gravity. Actually, this is not yet gravity. It is repelling. It is physically repelling with electromagnetic fields off of the table, but that's still potentially useful for engineering purposes. So, I
Dude,
mean,
all the science we can
especially
learn,
because with the system, you can get higher efficiency than with eddy currents. And so, if you've seen, there's someone online who made like a quadcopter with
Mhm.
eddy currents. They had some big neodymium magnets, and they were levitating this thing on the table.
Yeah.
Yeah, you can do that with magnetic fields and a metal because the eddy currents, the current in the table from the metal that's conducting is moving around slower than the magnet itself. And because it's lagging, you can actually have a repulsion between the two fields. Same idea here. You have an electrostatic field in the table, and that's lagging behind the coil, and that's causing repulsion instead of attraction. And
that sounds like just sorry to cut you off, but it's like from what I remember, this was communicate when I did maintenance. I used to say it's like, well, warm air rises. It's like no. Cool air technically falls because there's less energy. Anytime you have something that's more energetic, it's probably something completely different.
it's a duality. I mean, if you're talking about like they both happen. So they're from one perspective, it's happening one way. From the other perspective, it's happening the other.
You just cinched the knot in my head. This is a beautiful thing.
So anyway,
okay.
What was I saying? So the recent patent by Salvatore Pais has some cones that rotate opposite to each other. And these cones have high voltage AC and they have high voltage DC, and they have a coating of ferroelectric material. Typically, the response time of ferroelectrics is very fast. But when you have AC and DC fields together, you can kind of force it to lag behind the fields of the cones. So that patent is claiming that you have gravitational repulsion between the cones, but really you have electrostatic repulsion. I know this because I talked to some guys in the Navy and gave them the similar idea because I had no time to work on it, and I figured they could figure it out. And then this patent comes out a couple of years later. So, I mean, I wonder if there's a connection there. But yeah, I mean, ultimately, you can do that with electrostatic fields. You don't need, because if you look at what they're saying, these two cones have like a giga electron volt between them, and they're a couple centimeters apart, which means you're going to have 60 something giganewtons between these two cones. They're just going to slam together. There's no mechanical, not even diamond could keep those apart. So you need to create a repelling field in order to stabilize that fuser. And this is the way you do that.
This is fascinating. You've given me so much that I need to explore.
Mm-hmm.
So much time, so little to do. Wait, strike that. Reverse it. But Mike, hey, thank you so much. I'll add this stuff in the doobly doo. Actually, let me just toss it right there into the chat. So anyone that wants to and check out what we were just looking at, they can feel free to take a look. But other than that, Mike, thank you so much for joining me. And again, it has been yet to be proven
It's
that.
turtles all the way down.
Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.